Welcome back to Introduction to CFD. I'm Professor Steve Miller at the University of Florida, Department of Mechanical and Aerospace Engineering. In the previous class, we talked about who I am and my background and my own interest in research, so you got a better idea who I am. And we talked about the entire CFD class overview. This is an introduction to CFD class for aerospace engineers primarily, but we get students from all kinds of discipline, but we always have like an aerospace focus in the class. We talked offline about the syllabus, but I did briefly talk about its overview in the previous class. We talked a little bit about the course dichotomy and the course philosophy. That is, the dichotomy is that we're torn between learning to use one particular CFD solver and also understanding the theory and motivation and technical details of CFD. The major lessons of this course, which we outlined in the previous class, were that CFD has three major steps. The first is the pre-process, the second is the solution phase, and the third is the post-process and visualization phase. And we'll be looking at these through the class. The second major lesson I hope that students take away from this class is skepticism. And that doesn't mean that I just deny something exists entirely. No, it means that I'm skeptical of the CFD results themselves. And I ask questions like, how do I know they're correct? What is the process for producing them? What is the uncertainty of the results? And in this course, we'll look at ways to quantify that and reduce our skepticism of the validity of the results. In this class, we do look at some commercial solvers, but we're primarily looking at some open source free solvers that we can look at the source code and can be freely downloaded from the internet. Previously, this class focused on star CCDM, and we've transitioned to open source solver for what I believe is the benefit of the students. We also talked about the basics of CFD, who, what, where, why, and when should CFD be used. And we also talked about just about my perspective and philosophy on this class after performing CFD in government and university research labs for about the past 20 years. Every class I give a class outline. Here's this course's outline. This course is basically a crash course in computational fluid dynamics. Today we'll be looking at and just discussing a tip of the iceberg of these following topics: the equations of motion and their discretization. So equations of motion are just the physical laws written in a mathematical form. For example, conservation of mass, momentum, and energy, and perhaps a gas law, and any other types of sets of equations or reductions of those equations you might look at. Discretization of the equations is how we take these equations written in the continuum domain, if you will, and convert them into a discrete form for discrete mathematics, which can be evaluated by computers. Because computers are digital, they are essentially doing and evaluating discrete mathematics for us in computational fluid dynamics. Then we'll look at a little more detail with some visualizations of the three major steps of CFD: the pre-process, the solver, and the post-processor. In particular, we're looking at geometry and computational grid generation. What are those two things in the pre-process phase? Of course, geometry represents something about the fluid domain. It might be in 1 dimension, 2 dimension, 3 dimension, and it could be in like a space-time. And of course, some people doing more theoretical work might be looking at higher dimension fluid dynamics. Computational grid generation is where most people spend their time in computational fluid dynamics, and this is no different. So this is where we're creating the grid points and connectivity, which is used to discretize the equations of motion into the computational domain. Then the next step, of course, is the solver. This is where we take the discretized equations and solve the actual math problem. And this is done through linear solvers if it's a linear problem, and nonlinear solvers generally if it's a nonlinear problem. Then we'll look at two of the major important properties of the solution property process, which is, of course, convergence and stability, and some other properties too. Then finally, we'll look at the post-processing phase, which a lot of students initially think is where all the fun is, and it's true, it is fun. That involves like inspection of the solution. How do we take these field variables, the velocities, the densities, the pressures, temperatures of the fluid, and examine them and make sense of them. And of course, calculate derived quantities like lift and drag and vorticity, etc. Finally, we might look at how those results are graphed. And there's many types of graphs, which we'll be looking in this class. There's lines, there's scatters, there's contours, there's isosurfaces, animations, and we'll look at those in this class too. Crash course in CFD. This slide shows the most basic CFD process. The figure in the lower part of the slide is adapted from the star solver, and it shows the three major steps from their perspective. The first, of course, is the pre-process phase, where you find some geometry, you set boundary conditions, you create the computational domain. The second major step is the solver, where it takes the boundary condition and the discretized form of the equations and solves them in time or finds a steady time invariant solution. The third phase is that analysis step. This is illustrated in the flow chart on the right from pre-process solver to post-process. They draw a feedback loop because sometimes you need to feedback over that pre-process solver post-process case. Generally, for every geometry you have, every type of flow speed, wall conditions, or any other types of boundary conditions or initial conditions of the flow, how the flow initially starts, you might have to do another individual CFD run, and you repeat this process for every solution that you want. So what is CFD? This is where I'm defining it specifically, and that's right up here at the top of the slide. And it says, of course, that CFD is numerically solving an equation or set of equations that govern fluid motion. And throughout this class, this represents our definition. The second thing is always to keep in mind in this class and in your future careers, no matter what field you're in, is this skepticism. And always say through every part of this process, is this correct? Is there something here that's violating physics? Even if I'm kind of finding a solution which seems to be converged, which we'll talk about convergence later in this class, is it correct? And keep that in mind. We can't lose that. In many of your studies, you've looked at systems of equations for fluid dynamics or other physics problems, if you will, and in engineering, like in statics and dynamics, mechanics and materials. And it's a lot about developing some physical system and reducing to something that we can solve analytically. Here, we're not so much interested in reducing equation to some analytical form, but we do need to look at the major governing equations of motion. This is why your fluid dynamics or aerodynamics classes are so essential, because in these classes, they should have showed you how to develop the Navier-Stokes equations. So the Navier-Stokes equations are generally equations that govern fluid motion are systems of partial differential equations. And in the lower left corner of this slide, I show one set of very famous and popular equations, which are called the Navier-Stokes equations in one particular form. And of course, these are subject to particular boundary conditions. Boundary conditions are what we're setting the value of the field variables, that is densities, velocities, pressures, temperatures, or other quantities of interest, which are interesting to find, or something about them on the boundaries of the domain. Remember, initial conditions are what these field variables are within the domain. So for a given boundary condition and domain, the system of equations may or may not have analytical solutions. We don't know if the solutions exist. We don't know necessarily if they blow up to infinity or not. Obviously in nature, we know they generally don't in a fluid, but mathematics is a different animal, so to speak. And it could be that the equations, the way we've written them down, may not have a solution, or even a numerical solution. And this is back to the idea if equations are well posed or not. Generally, for the problems we're looking at in this class, they should have solutions. After all, we do observe them in nature. And the question comes back to if the equations are valid to model what's happening physically in nature or in our experimental wind tunnel, for instance. Unfortunately, a lot of these equations are so complicated, like you see in the lower left, that they may not have necessarily analytical solution or even an approximation of that analytical solution that we can find. And so we're forced to use computers because we can't solve these sets of equations analytically for given boundary conditions for cases that we're interested in, like a high-speed turbulent flow in aerospace, we have to solve them numerically with digital computers. And that's where computational fluid dynamics comes in. That's why we do computational fluid dynamics, because we are not, frankly, smart enough to solve these equations analytically. But maybe I should only speak for myself. Perhaps one of the students in this class one day will find or advance the mathematical theory of partial differential equations, where we can be less reliant on CFD, and that would be a wonderful contribution. The equations in the lower left are 3 sets of individual partial differential equations, and they make up a set of partial differential equations. I'm hopeful that you can recognize them in their form. The first equation represents continuity. That's the conservation of mass. The second equation represents the conservation of momentum. And the third equation is a form of the energy equation, which is an expression of the first law of thermodynamics. Sets of equations, but they're not closed. They need a gas law. For example, like the perfect gas law, P equals rho RT to close them. Now let's just remind you, I hope, of the notation of these equations. So these little first symbols here are partial symbols, and that means it's the partial derivative of this variable rho with respect to time. So that's just the derivative of rho with respect to time, plus the partial derivative, of rho times u with respect to x. And I'll explain these subscripts in a second, and it's equal to 0. So in this class, and in the fluid dynamics community in general, we express rho as density. So if previously your professor or in your reading you missed that rho is density, here it is. It'll remain density through the class. U will be velocity. The sub j indicates which direction the velocity is in this case. J equals 1 would be in the x direction, j equals 2 the y direction, and j equals 3 the z direction of the velocity components. In the second equation, we have some other variables we haven't defined yet. There's P, that is the static thermodynamic pressure. So that's the internal stress of the fluid. Tau sub ij is stress tensor, so that's the stress on the fluid's surface in the normal and shear directions. So if I equals j here, it's in a normal direction. If I and j equals 2, for example, it'd be the normal stress in the y direction. In the third equation, E will be an energy, and Q will be a heat transfer term. And I think that's all the variables. You notice that capital T doesn't appear in the equations. We'll say that capital T in this class is for static thermodynamic temperature. Now you might be wondering why these little j's are also on the x variables. Well, that's because it is a Einstein index notation. So x sub j equals 1 would be the x direction, x sub j equals 2 would be the y direction, and finally x sub j equals 3 would be the z direction. Oh, and excuse me, I forgot to define this variable here, this delta sub ij. That's what we call the Kronecker delta function. And it's very simple. If I equals 1 and j equals 2, then it is 0. If I equals 1, if j equals 3, it is 0. If j equals 2, if I equals 1, is 0. So the Kronecker delta function is 1 if I equals j, and 0 if I is not equal to j. Let us explain the Einstein index notation. Here in these equations, I have subscripts I and j. I've already discussed how they correspond to particular directions in the coordinate system. Now, there's a rule in this so-called index or Einstein notation, and on the class website I've pasted a document that explains all this in greater detail, which I encourage you to look at. If two indices are repeated in the same term, for example, this is term 1, there's no indices, this is term 2, and it's equal to 0. This is conservation of mass. If two terms like j and j appear in the same term, or I and I, they're repeated over the number of dimensions. If we're in 3 dimensions, these would be repeated 3 times. So this second term would be written partial rho u1 partial x1 plus partial rho u2 partial x2 plus partial rho u3 partial x3. So expanding out this term actually gives us three terms. If we write it as the velocity vector u equals uvw for the three directions of components in the velocity, it'd be partial rho u partial x plus partial rho v partial y plus partial rho w partial z. In your homework, and here I encourage you to stop and write out these terms. Now you say, oh, well, Professor Miller, some of these terms have two j's, for example, and I. Well, here's the trick from the momentum equations, because of course we need to know that this is really three equations. It's a vector equation, so it'd be three scalar equations, if you will, and a single vector equation. So the first term only has a single index I, so let us set that to 1. And we set I equals to 1 in all the other terms. So for example, the third term, the pressure gradient term, would be negative partial p partial x1 delta 1j. Now in this term, you see that there's two j's. So I would sum over them for the I equals 1 equation. This is the x direction conservation of momentum equation. That's negative partial p partial xj, or now it's going to be x1, delta 1, 1. So that's delta I equals 1, j equals 1. Negative partial p partial x1 delta I equals 1, j equals 1. Remember Kronecker delta function, if I equals 1, j equals 1, then it's 1. So the three expanded terms of this third term in the momentum equation would just be the first one for I equals 1, j equals 1, because the second and third terms for Kronecker delta function would be 0. Let's look at I equals 2, this y direction scalar conservation of momentum equation. The same rules apply to the energy equation for expanding the terms. We'll look at most equations in this class in the index or Einstein notation. So please pay special attention to these rules because they'll be used throughout the class. And they're used predominantly in the research, industrial, and government communities of computational fluid dynamics. You'll be expected to see these equations and understand how they're expanded and what they physically mean. I've now explained the heart and core of CFD, that there's some system of equations which are discretized and then subsequently solved with a computer. Now that can be done, that solution process, by many types of computational fluid dynamics codes. This slide just explains the types of codes and their classifications. I define a CFD code as a suite of computer programs or program that solves computational fluid dynamics or a portion of the program. There's many types of solvers. For example, commercial CFD codes usually provide all these set of suites as a single package, which you, of course, have a license. That means you pay money for, usually on a yearly or monthly basis, or sometimes on a time basis, the number of hours you use it. So these codes contain preprocessor solver, the actual solver, which is the actual CFD code, and the post-processor. And these all work seamlessly in one program. These can be shown in the figures on the right here. This is from the Star CCM software running on Windows. And you can see there's some contour plots here, so it's showing the solutions. And these might be recognizable to you. What might you think the upper one might be? Well, from experience, I recognize that right away as some sort of flow moving from left to right that's supersonic. And this red line here would be a shock wave. This sort of larger contour range would be an expansion wave. And then this little corner here, which the flow turns into itself one more time, would be a second trailing shock wave. So this is a typical supersonic flow problem where we have some analytical solutions, for the inviscid case at least, meaning there's viscosity set to 0, and it's solved with Star CCM. So this is a typical window you might see. And a lot of this commercial software works the same. There's usually some sort of options here on the left, and somewhat like a CAD software too. The lower image you might think of as like this is some sort of pipe flow. So of course the flow moves left and then right, and they're looking at some geometry of it, not solutions. So they contain everything from going from like rudimentary CAD and CAD import to creating the computational grid, to discretizing the equations, to solving them, and then visualizing the results, like in the top image. So these commercial codes provide all that in one seamless package that you can use. I personally think it's better to learn using individual packages so you can focus on each part of the solution process. If you just want to create CFD cases and just do CFD and don't care what's going on behind the hood, I suppose that's fine, but those users can be dangerous because they don't understand the mathematics and physics of their choices, and they are often surprised and bewildered when something goes wrong. So we'll try and avoid that through teaching you this method within this class. Often CFD codes integrate into a larger CFD company, and we talked about this in a previous class, and it might be also fine in like small groups. CFD is used in our student groups here at our university, and of course it's used in government and in research. So it can be CFD is something you might do on your own or by yourself, and all the way up to large teams. It is critical in today's aerospace industry. In this particular class, we're using a number of open source and free software codes, which I'm talking about in our class discussions. These codes are typically available from governments, from universities, and some industries release their codes. Often government codes are restricted because they might be doing critical calculations for the aerospace industry, which are classified, or they might be internal to companies such as like Boeing or Lockheed Martin or a number of other aerospace companies. And these are perhaps seen as trade secrets or copyrightable software, and they're very hard to get a hold of as like a user outside of those companies or governments. Universities are much more open about our codes, and a lot of research groups share our codes freely online. For example, one of my students has shared his one particular type of code, a spectral large eddy simulation code, on the internet for free for anybody to use. So there's different kinds of communities, and codes, because they're validated and written over decades sometimes, are very, very valuable, but know that they all follow the same process. And if you learn one approach, it's very, very easy to learn another. For example, if you use a commercial solver, I think it's a little bit harder to learn research solvers because they work a little bit differently. And if you learn sort of research and developmental solvers, it's much easier to learn a commercial code. And we'll be learning sort of a research open source solvers in this course for your advantage. Remember, in computational fluid dynamics and engineering, or maybe life in general, the hardest part is defining the problem. So before you try out any CFD, please try and understand, and this is the approach we'll use in this class, of understanding the underlying physics. If you don't understand the equations you're solving, there's almost no point in solving them numerically because you can't understand the results and solutions of those equations, the numerical solutions. Before you even do CFD, think about if it's the appropriate tool, because today, for engineering design, CFD is one of many, many tools. So check if an analytical solution exists for your case or not. Is most likely not available. Or maybe there's some other method that is more appropriate to study the problem. Perhaps it's just better to go into a wind tunnel and do an experiment, if that's even feasible. Perhaps it's easier to look up literature. Maybe other people have studied the problem. If you have decided that CFD is a good idea, then you'll have to look at and understand the type of flow fields you might get. That is, if you have some domain and boundary conditions and certain speeds. Once you've decided you want to do CFD and it's appropriate to solve the problem, then you'll have to think about what kind of flow it is, because these will dictate choices of the type of CFD solver you use, what kind of boundary conditions to set, what kind of assumptions are in the equations of motion, if you need a turbulence model or not, what are the Reynolds numbers, and there'll be best practices for this. The only way to do this starting out is to talk to other people or look at literature online to see how other researchers have studied the problem. But this will come with experience, and you'll find your own set of best practices. So I've given some examples of this in bullet number 4 here. You might classify your solution. Is the flow laminar or turbulent? That is, are there chaotic fluctuations in the flow, or is it a nice smooth creeping flow? Is the flow incompressible or compressible? And this is a huge choice. if the flow is compressible versus incompressible, then you'll have to almost choose completely different solvers in CFD. That is the way we are solving the equations of motion. Is the flow statistically stationary or steady, or is it an unsteady flow? An unsteady solver needs to resolve the temporal fluctuations in the flow. A steady solver, of course, assumes that these fluctuations about like some base flow, for instance, are zero, and it's more appropriate to choose the steady option. Steady solvers are cheaper. And in this class, we're mostly going to be looking at steady fluid dynamics problems. That doesn't mean that they're not turbulent and they don't have temporal fluctuations. And we'll talk more about why we make these choices in the class. So you have to choose the solvers accordingly. That's why in this class we will discuss the algorithms and underlying theory and implementation and the advantages and disadvantages of these types of solvers for CFD. If you are able to get results from the CFD run, you need to verify that they are correct and validate them in some way. That leads into skepticism. How do I know that my results are correct? How do I know that my solver is even working correctly? You might run it against benchmark cases that you know solutions to, like analytical solutions, or compare them with some baseline experiments. And that is done on a regular basis with CFD solvers and development groups, and is certainly done in production and industry where people want to make sure that they're running the solvers correctly, because they're obviously very large and complex systems, as you're starting to see in the class. We've talked about one set of equations, the Navier-Stokes equations, and we discussed very briefly the idea of how they're discretized. Recall that we discretize them on points, for example, called grid points. These are the discrete points in space where we want to find the solution. That's very confusing. This isn't like a typical differential equations class where we have a single differential equation, we have some boundary conditions, and we solve it, and we know the solution everywhere, and it's an analytical solution that we can put back into the original equation with appropriate boundary conditions and verify that it's a solution. This is not really possible to do in CFD or any numerical method directly. And we'll talk about this process in a little bit. The next question you might have is, if we discretize the equations and we're finding the solutions on particular points in some domain, how do we choose where the points are? How do we make this system of points in space? That's the idea of grid generation, which is part of pre-processing. In the pre-processing phase, you'll have some discretized forms of the partial differential equations, and they must be solved at these discrete points. We call these discrete points grid points. Now, we might also have what we call a volumetric formulation where we find the solutions within volumes. This is typically how you're taught to find, say, Reynolds transport theory, or the volumetric forms of the equations of motion, in your introductory fluid dynamics or aerodynamics classes. So the discretized equations are solved on grid points or within volumes of elements or cells. Now, these grid points or volumes obviously must conform to the boundary of your physical domain. Let's look at this in example so it makes a little bit more sense. In the lower left of this slide, we have the physical domain, and I colored it in blue. It's arbitrarily shaped. So the blue area might represent your liquid, your gas, or your plasma. The edge or boundary of this physical domain is the outline. These are the edges. So for example, we might want to say, hey, this is a fluid, and we want to know the motion of the fluid given some boundary conditions. The boundary conditions are along the edge of the physical domain. So this could be a boundary condition all along here. And we can tell, we decide what the boundary conditions are. For example, these might be a wall with a no slip condition, and this might be another wall with a slip condition. This could be where the flow enters the domain and where the flow exits the domain. the solution might look like, hey, there's some velocity vector or streamline coming through the domain from left to right. We can also set boundary conditions in a different way. Perhaps these two walls are inlet boundary conditions that are supersonic, so the flow enters the domain from left to right supersonically, and these boundaries here on the right are an outlet, meaning the flow can exit the domain here. This lower boundary could be set to a wall, and the flow would come in left to right once again. So for the same physical domain, we can set different boundary conditions to dictate, in a sense, the solution of the problem. The boundary conditions should somehow be represented as something physical. Now, to enforce the boundary conditions, you have to know something about the solution at the boundaries. And so you would want to know particular solutions at discrete points along each boundary. You would want to put grid points along the edge of the physical domain so that we can enforce and know the solution on the edges of the physical domain. We would also have to put grid points within the domain. Why? Because we need to enforce the partial differential equations within the whole domain. We can't just put points along the edges and discretize our set of equations with large delta x's across the domain. Remember, we would ideally let that limit of the discretization become very, very, very small so that we can approximate the partial derivatives. Let's go back a few slides just to look at that again. Remember this equation. Here's the delta x between grid points. It needs to be very, very small for this limit to approximate the actual partial derivative of the equations of motion shown on slide 5. We would need to put grid points within the domain to resolve the flow. Generally, the more grid points or discretization points within the domain you have, the more accurate solution you have, because you're letting that delta x become smaller and smaller. So this on the left is the physical domain, and on the right we have the corresponding computational domain. And here you can see I have labeled what we call grid points or nodes, depending on your community, as little blue dots. I have labeled the lines as connectivity. So connectivity is how all the grid points or nodes are connected in space. Now, look at the comparison between the physical domain and computational domain. I have made a very, very coarse domain of little grid points on the edge of the domain. And see this top wall, I've actually put 3. So I've discretized this as 3 particular points. I've also put grid points internal to the fluid volume. I have 1, 2, 3, 4, 5. This is not many grid points, especially because today a contemporary case might have billions of grid points to discretize the physical domain. I've also put in connectivity between all these grid points. And you'll see that some of the cells or elements made up of the connectivity of 3 nodes are, for example, little triangles or other shapes. And of course, you can have all kinds of arbitrary shapes with as many sides as you want. But it may be very difficult for your solver, if not impossible, because it's not programmed in the solver, to have arbitrary shapes of these elements in your domain. At the end of the day, you need to have grid points and connectivity that takes the physical domain and is representative of it in the computational domain. You'll also notice that these nodes are not necessarily at the same spacing delta x and delta y and delta z. And you'll also notice that there's all kinds of different element shapes. So the finite difference discretization technique I showed earlier would not be appropriate for this type of computational domain. I have to have a different type of discretization technique than the finite difference approach. What would be appropriate is the finite volume or finite element approach to find a solution for this type of computational domain. We call this an unstructured computational domain. We're going to look at a lot of the grid generation approaches for structured and unstructured computational domain in the next module of this class, which is called grid generation. So remember, at this point, you should know that your CFD solver is going to either find the solution of the field variables at the nodes or within the elemental volumes, or if it's finite element, and actually can find them within more points within the volumes that we'll talk about more of that later too. Talked a little bit about the equations of motion and their discretization onto points and nodes. And now we need to talk about the pre-processing phase of CFD. So remember, grid points and their connectivity in a computational domain where the solver finds the solutions now easily number in the billions for large contemporary CFD cases. Some of my students are making computational grids in the millions, if not hundreds of millions. And there is a large field of mathematics and engineering to create software and the algorithms behind creating these computational domains very quickly. You can see that for a given geometry or physical domain, there's basically an infinite number of types of computational domains you can create. So you'll have to ask yourself, what is optimal? You typically want to generate these computational domains with the least number of grid points possible. Why is that? Because for every grid point, you need to have some amount of RAM used in the computer to store its information. The more grid points you have, the more RAM you use, and the longer the solver has to take to solve and find a solution. These are often made by companies, but thankfully today there's also some open source software to do this, and we're going to be trying some of the free and open source software to save a little bit of finances for our students. Generally, the more grid points or volumes in the grid you have, the better. And it should converge closer to the solution, which we'll talk about in a few minutes. Of course, the more grid points you have, the more resources you use in the computer. The longer your solver takes, the more RAM you need. So there's a balance between wanting to add more and more grid points to the solution to refine it, and of course, the computational cost, which translates into money. Generally, there's sometimes very expensive software, but very, very good software designed to create these domains. On the right here, I have a figure of another computational domain, much like the one shown on the previous slide. The black box represents the outer boundary of the domain, and this inner white structure just represents some aerodynamic body. Looking at this, you could imagine maybe flow goes from left to right, and this could be like the cockpit and nose cone of some type of aircraft. Where every little line intersects is a node in the computational domain. The lines between each node represents the connectivity. So we have a system of hundreds of triangles with connectivity and nodes. And this particular case, if it was a finite element solver, we might be finding the solutions at every node. If it's a finite volume solver, we might be finding the solutions within every little triangle. So there was a little computer program written that generated the grid points and connectivity for this domain. We'll be looking at those algorithms and computer programs within this class. The next phase, once we've discretized our equations and created the computational domain and set the boundary conditions, is to solve that set of discretized equations. This is a solver or main heart of CFD. So typically the solvers are responsible for finding the solution of the discretized form of the equation. When the solver is finished, it might write this as a solution file which can be visualized with your visualization software. It only usually consists as the field variables, which are densities, the velocities, pressures, temperatures, etc. Only the variables that are being used and solved in the computer are written to disk. You'll have to find those other variables in the post-processing phase. It's an extremely complicated and difficult subject to create these numerical solvers that have been happening for decades, even before the invention of digital computers. And you can imagine in your numerical methods class, you learned about something like Euler's method or Newton's method for finding roots. Well, these are basic numerical algorithms and solvers to find, say, a zero of a function or to discretize some equation to find an approximate numerical solution. Those are the types of algorithms and equations developed to find numerical solutions that were done by hand. We're doing the exact same thing, but with much more complicated algorithms on our digital computers. These solvers and the way to solve the discretized equations are written as mathematical algorithms. And today they're typically written in high-performance computing languages. And the most popular one for supercomputing or parallel computing is the languages of C, and Fortran. C and Fortran were two of the original programming languages. Fortran was one of the first compiled languages written specifically for engineers and mathematicians to solve equations for fluid dynamics. And there's extra work to be done today with parallel computing. So if your computer has multiple processors in it, we have to find ways for those processors to communicate to each other. There's a few different libraries that hook into C or Fortran. For example, these might be the Message Passing Interface, MPI, or it could be OpenMP. These are two freely available parallel algorithms developed mainly by governments and university researchers throughout the world and used almost universally for high performance calculations. Now you could easily program solvers and all these algorithms in interpreted languages like MATLAB or Python, but unfortunately they're very slow to run. And if you're using one of the world's largest computers to do a CFD calculation, you certainly cannot sacrifice performance with MATLAB or Python, for example. So predominantly high performance and well-written professional CFD codes are written in very fast compiled languages like C and Fortran. If they run slower, then unfortunately you're just costing money. And it could be that the problem isn't even solvable using something like MATLAB, as it can't scale well to a supercomputer. In this class, we're going to cover a number of solvers and their discretization schemes in terms of their equations and algorithms. And here's just a few I'm listing up here in the upper left. We'll divide these in incompressible algorithms, which are designed to quickly and efficiently solve discretized equations for incompressible flows where the density isn't changing. Then the second class of solvers we'll look at are, of course, more general because you haven't made the incompressible assumption, but they're designed more so for compressible flows where there's high compressibility. And these might be called something like ACM or simple or piezo, the piezo algorithm, which is modified for compressibility. We'll talk about preconditioning for creeping flows and very, very high-speed flows, and the FDV algorithm. These are generally acronyms, and we'll talk about each algorithm and solver throughout the class and talk about its pros and cons and what kind of flows they're most adaptable for. The wonderful thing about CFD and some of these codes is these algorithms are integrated in solvers. So once you choose your set of equations like Euler or Navier-Stokes or some potential flow solver, you can change the solver and see how it affects the solution, or even if you get a solution or not. So with just a few clicks of a mouse or a few changes in a command line in your input text file for your solver, you can try these different algorithms. What will happen? Well, sometimes you'll get a solution very fast, or maybe you'll get a solution and it's not really correct. Maybe you won't get a solution at all and you'll just get not a number or infinity or negative infinity. That means your solver, of course, is diverged. The solution is blown up and the numerical solver or algorithm is unstable. So we'll see all these cases in this class. One major point which I want you to take away is that these algorithms are computationally expensive. The more computer time you use, it could be hundreds of thousands of wall clock hours if you're doing large calculations, directly translates into money. Why? Because the computers cost money, the people to maintain the computers cost money, and of course it's your time too, which costs money. So the more time the solver takes to find a solution, the more power it uses, and the more power it uses, the more your electric bill will be. And so some of these large supercomputing centers have large teams of dedicated engineers, computer scientists. Of course, the computing vending companies are integrally involved in these operations, and it comes out to be many, many, many millions of dollars per year just to operate these supercomputers. Of course, in this class, we've designed it so that you can run the geometry the preprocessor, the solver, and the postprocessor all on your personal laptops. So we've kept the cost to a minimum, and we don't even have a license for solver. The advantage of this approach is that it's low risk. So when you make mistakes learning CFD, and you will, and that's okay, that's how you learn, it won't be costing you large amounts of time and money. And we've also broken down the process in tiny little pieces. And we'll learn each little piece on its own individually and build it up to be a system of solvers where you can go in and define the problem, create the grid, boundary conditions, solve, post-process. About the solver, remember, it is finding numerical or discretized equations of the equations of motion. So there's many choices of equations to solve, and I've already named a few here. There's the Navier-Stokes equations, the Euler equations, for example. That's just two. And there's many types of equations we can choose to solve in fluid dynamics, and we'll be talking about those in this class. Often there's a turbulence model involved. Turbulence modeling is a very complicated subject, and we'll be talking about that later in this class. But basically, it's giving some model to the code to reduce computational expense to resolve the turbulence. That's the bottom line. Another unfortunate thing about turbulence modeling, which is to do with what we call the closure problem, is that there will be more unknowns with a turbulence model and the equations of motion than there are equations. And so a major component of turbulence modeling is to create or modify sets of equations to close the set of equations so they can be solved discretely in a CFD code. This constitutes what is really traditional CFD turbulence modeling and what we'll be doing in our class. We'll be exercising those types of models. There's other types of techniques and models, but unfortunately they're much too computationally expensive to try in the class. But we will talk about their theory and what they are and how they're used. Unfortunately, these types of models can't run efficiently on our laptops to learn. What is important for you as a researcher and student is to say, okay, there's many types of equations and many types of models to choose from. For each of these, it's important that you know what assumptions go into these equations and models, and to know when the equations and models are appropriate for different problems. If you choose a set of equations with some assumptions and particular models to close them, if it's a turbulent modeled flow, then you're going to get a solution, but it'll be a wrong solution because you haven't put in and captured and accounted for the correct physics in the model. One example here is on the right. This is a simple smoke coming up next to an upside down spoon. So in this case, the flow is laminar initially. It comes up, it starts waving like there's a small instability, and it hits the spoon and it comes back around and it comes up into the air, into these beautiful, beautiful turbulent eddies that go up. So it's much fun to watch these flows. They're very aesthetically pleasing. But imagine you had to create a a numerical solution to this problem. So what might you do? You might look at this as the computational domain, and then there's certain boundary conditions. For here, for example, up on top, I would want the smoke to leave the domain, and down here, I would want the smoke to enter the domain. The spoon itself would be a boundary condition of a wall with no slip, for instance. And maybe there's no heat transfer. We could maybe say it's adiabatic. Anyway, the smoke would come up, and it would hit the spoon and comes around and becomes turbulent. So in this situation, I have a very, very difficult problem to solve numerically. I would have to, in terms of the equations of motion, decide if it's a turbulent problem or laminar problem or transitional. Those are the three types. Unfortunately, it contains all three. So you'll have to choose some sort of set of equations which can capture all this physics in one problem. And that is very difficult to do computationally. Even the simple spoon or wake problem, low speed turbulent problem. Let's talk about some properties of the solver. So here's some of our first important definitions, which pretty much everybody in CFD knows and understands and is essential. The first is stability, and let's read these together. Stability is the property of the solver where as it progresses towards finding the solution of the discretized equation, the error decays. So if we have a solver and it's iterating or trying to find a solution in time or through iterations, and the error grows, then it's unstable. Now, solvers might have error growing over a short amount of time or a short number of iterations. That's okay. We're really talking about global stability. So if the error goes to infinity over time, then the solver has blown up, it's unstable. So if the error continues to decay and become stable over a long time, the solver is stable. The next definition is also important: consistency. If a finite difference representation of the partial differential equation is consistent with the difference between the PDE and its discretized form, representation vanishes as the mesh is refined. So what does this mean? If I have a discretized set of equations and a continuum set of equations, the original set of equations, and if I find the solution in the discretized set and the continuum set, and I let the delta x, or grid point spacing, in the discretized set of equations go to 0 or become very small, then the two solutions will be the same, or vanishing as the delta x becomes very, very small. This is the idea of consistency, that the discretized form of the PDE is going to give the same solution as the original PDE with diminishing grid point spacing. And it's that simple for consistency. If we have both the properties of stability and consistency, then we have the property of convergence. What is convergence? Convergence means that the discretized form of the equations in motion will approach that of the governing equations as the mesh is refined and the solver progresses. So convergence is the combination of the properties of stability and consistency. On the figure here on the right, you see an x-axis, which is iteration, and a y-axis of residual. Residual is a type of error estimate, which we'll talk about later. The other y-axis is the error, which is, of course, the difference between the discretized solution and the analytical solution. On the x-axis is iteration. So this means for higher iterations, the solver has approached and trying to estimate more accurate solution in terms of reducing the error and comparing it to analytical solution. The lines on these graphs just represent different types of solvers, and you can see that there's many types of solvers in this class. For example, MG represents multigrid as one of many examples, and these lines are plotted. So for the same problem, the same boundary conditions, the same discretization, we can run different solvers and we can reduce the error at different rates. Of course, on a per iteration basis, it might cost more or less computational time to go to the next iteration. So that makes it a difficulty. It's not truly a one-to-one comparison. But for the same number of iterations, you can see some solvers have reduced the error of our solution at a much better rate, if you will. And we'll be talking about the advantages and disadvantages of these in this class. Once we found that numerical solution, we can post-process the results. So post-process, remember, involves analysis, examination of the solution, plotting the results, visualizing the solutions, and these are all extracted from the field variables which are found from the solver. Typically in a numerical database, the solutions are, of course, the discretized equations. So remember, you're visualizing the numerical result, the discretized result. Visualization itself means a graphical or other representation of the solution for understanding the physics and implementation of the results. So the visualization is taking that numerical database generated by the solver and interpreting it. So this is quite the fun part of computational fluid dynamics. Extraction is the process of deriving quantities or other qualitative flow physics from the CFD solution. So that could be where you're doing additional math, which I'll talk about in a second, based on the numerical solution. For example, if you want to find drag or lift, you'd be integrating quantities of shear stress and pressure on, say, an airfoil. That's part of a post-processing system, for example. It's doing a little bit of extra math with the numerical solution to find results that you want. Typically, these processes are automated in many solvers, but sometimes you actually have to program the equations and algorithms in a computer program that can find these quantities for you. And this is typically done in research environments and many other environments, like in government and industry. We typically view these CFD solutions through graphs, and there's many types of graphs like line plots, contour plots, or even something more complicated. And here's an example on the right from the Combustion Research Facility at Sandia National Labs. So what are we seeing here? The black plane represents perhaps the ground, and then you see all these colors. And what's happening is there's a flow coming up through a little round hole in the ground. It's coming up and it's going into a crosswind, which goes from the lower left of the image to the upper right. There's all these like little tubes, and these tubes are isosurfaces. They're just surfaces that exist in space that all have the same property of some quantity. The particular quantity shown here, I believe, is the Q criterion. We'll talk about Q criterion later in this class and make some visualizations like this later on. The colors of the isosurfaces are something else. They might correspond to pressures or velocities or some other quantity. So this represents a CFD simulation in 3 dimensions. It's time dependent. It probably uses some sort of turbulence model within it. So it's simply a jet and a crossflow. Where might you see those in nature? Well, of course, you might see them at the bottom of a sea floor. So it could be if oil is coming out of the sea floor through like an undersea tube, like for example, oil in a Gulf spill. It could be when you're driving down the highway or bus or plane and you look out the window and you see a smokestack and you see the smoke going out into the atmosphere, and the wind is, of course, from the atmosphere. Those are just 2 cases of many where jets and crossflow are very important, and you can study those with CFD. Let's look at just a few more examples of post-processing results and graphing results. Of course, there's many types of graphs. Some are more helpful than others. So as an engineer, you'll have to decide what types of graphs do I want to create to convey the physics of the flow and quantitative information to my intended audience. Your audience could be the general public, or it could be other engineers or mathematicians or physicists, and you'll have to choose the right tools, the right quantities to show. Now, there's pros and cons to each type of graph. Some graphs are more qualitative and some are much more quantitative. So on the right, you might look at one example, and this one's from NOAA, which is a federal government agency, which does, of course, hurricane prediction. And here's one particular plot. And what you're seeing are contours. And what are the contours? The contour bars on the right. So this is somewhat quantitative because they've labeled the contours of the quantities of the contours. They've also given isosurface to these contours as black lines, and they've labeled the black lines with pressure values. And of course, they've also overlaid the United States as black lines, both the coast and the state borders. So this can quickly give an idea to the general public with some idea of wind speeds and pressures about what they might be experiencing now and within the future. So you can see this is a combination of quantitative and qualitative graph made for the general public. It's not the best graph for telling me exact quantitative information, which might be the actual numerical data, but that might be too much for me as a human being to interpret. So I maybe make a line plot, and that would actually tell me the exact values if the figure labels are adequately defined to tell me what those values are at some particular point or height in the atmosphere. So there's all kinds of ways to make these graphs, and there's appropriate graphs for different situations and audiences. We'll talk about all this and make some of these graphs in this class in the visualization module. If you have a CFD solution, if you post-processed it, you might only have at hand the densities, the velocity components, and pressure and temperature or energy. Fortunately, there's a lot of things in engineering that we might want to find that is very useful. For example, vorticity. In your fluid mechanics or aerodynamics class, I hope that you've talked about the importance of vorticity and what it is. As an example, remember omega, if it is vorticity, equals nambla cross u. This is written in this equation in the lower right, next to this figure. So circulation is an integration in space, or in some surface, or on a line, depending on how you define it, of vorticity. So here in the lower left, I give an example of a circulation calculation where I'm calculating the circulation on some plane. So the CFD solver is not going to give you circulation directly, and it's not going to give you vorticity directly. The first step would be to take the velocity components at every point in space and find nabla across u. Then I would do an integral of where I want to account for the circulation and the flow. This is one example of a derived quantity. You would also have to do this for lift, drag, something like entropy, which we'll talk about in this class, circulation, which I just showed a very brief example. But these can all be defined and derived from the CFD solution of the field variables itself. These derived quantities are also a CFD solution. However, they're done in the post-processing phase. Now, some people have integrated the calculation of these quantities into their solvers. In this class, our solver will be able to calculate some of these quantities during its run. And we can look at these quantities and how they change with time or iteration to decide if we have a solution that is valid or not. For example, if we have an airfoil at zero angle of attack and it's a steady flow, it should have no lift. So if our CFD solver is telling us that as a lift of 10,000 pound force, that would be very strange. It should be very, 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 very close to zero, if not negligible, if the solver is working correctly. So you can also use derived quantities or quantities of interest in your flow field to see if you have a valid solution or not. So in this class, we've looked and talked at a little bit more depth of the three major steps of CFD: the pre-process, the solver, and the post-processor. Throughout the class, I'll always be reminding you to be skeptical of the numerical results you generate and asking how you can reduce your skepticism. How can you reduce the error? How do you know if you have a physical solution or a converged solution? And remember the definition of stability and convergence. So in this class, please have fun exploring one contemporary CFD solver, and we'll be looking at this more in depth throughout the class. Next time, we'll be talking about CFD itself, and we'll be looking at the solver we're using in this class. We'll be looking at some grid generation examples for the software using in this class, and we'll be looking at the visualization we're using in this class. So we're going to look at all three steps of CFD. I'm going to be showing you a lot of screenshots of the entire CFD process we talked about today. So in a way, it's going to be a virtual tutorial of the CFD process, and you'll also be doing these types of steps and runs throughout this class yourself. Thank you very much for your time today. I look forward to you next time.